Hello. Today we're going to be talking about the different topics that will be coming up on your next test. So test on Tuesday. So test number 1 will go over chapters 11, 12, and 13. 11 we talk about intermolecular forces and properties of pure substances. Chapter number 12 we talk about solids and their properties, and then chapter number 13 we talk about solutions and their properties. So they're fairly interrelated. So in this, one of your biggest resources to making sure that you know all the things for the test is looking at your different learning objectives. So all the learning objectives are posted online, so you can look at all of them for each lecture, and those will be kind of a guideline to what you need to know. But we'll look at some more specific things today as well. First, chapter 11. So we're going to start with chapter 11. We talk about intermolecular forces versus intramolecular forces. And you should know the difference between the two. Your intermolecular forces are going to be between two different molecules, while intramolecular are going to be between atoms within a molecule or compound. So intramolecular forces, we're talking about bonds, covalent bonds, ionic bonds, or metallic bonds. With intermolecular forces, we're talking about things like ion dipole, dipole forces. So things that hold different molecules or ions together. So intermolecular forces are weak, under 100 kilojoules per mole, while intramolecular can be anywhere between 100 and 5,000 kilojoules per mole, so significantly stronger. With our intermolecular forces, I'm going to go over some things that are also in chapter number 13, where we talk about solutions when I'm going through here, because I'm just going to go through all of our intermolecular forces that we looked at total. So from highest energy to lowest energy, our highest energy are ion dipole. Ion dipole are the strongest. They're between 10 and 100 kilojoules per mole. And this is between an ion and a polar molecule. So this is what we see in salt water. So how salt water makes a solution is through ion dipole interactions. So we have something like a sodium ion with a plus charge being attracted to the negative end of a water molecule. Right? And when we have these type of things occur, these interactions, these water molecules will form what's called a hydration sphere around these ions, and that's how we hydrate stuff like ions. We also call this solvation. Okay, our next slightly weaker force is going to be our hydrogen bonding. Hydrogen bonding is between two ultrapolar molecules. So two ultrapolar molecules are ones that have hydrogen oxygen, hydrogen nitrogen, or hydrogen fluorine bonds. Just to make that a little bit more in line. Okay, so our hydrogen bonding between a molecule with a hydrogen nitrogen, hydrogen oxygen, or hydrogen fluorine bond, and a nitrogen with a lone pair, oxygen with a lone pair, or fluorine with a lone pair. So we call them ultrapolar molecules because of anything that contains those things are going to be significantly more polar than things that do not. Hydrogen bonds themselves are pretty strong. They're a little bit weaker than our ion dipole, but still very, very strong. So it's a strong interaction. It varies quite a lot, but probably somewhere between 5 and 80 kilojoules per mole. Okay. The next thing we have that's a little bit weaker is going to be dipole-dipole interactions. So this is between two polar molecules. Oh, real quick, let me just write what a hydrogen bond would look like. So we can have something like water interacting with something like formaldehyde. So between this pair of electrons on this oxygen and this hydrogen attached to an oxygen. Okay. Dipole-dipole. Just a little bit. These are between two polar molecules. Dipole-dipole forces are kind of a weaker force. So it's going to be weaker than our hydrogen bonds. So this is going to be between 5 and 25 kilojoules per mole. And we have the partial positive end of one polar molecule interacting with the partial negative end of another. So let's look at formaldehyde again. So it's what formaldehyde looks like. This has a partial negative and a partial positive that will interact with another formaldehyde molecule. So this partial positive, this partial negative, like so. A little bit weaker than that, we have all of our London dispersion forces. So these are any of our forces where we have a temporary dipole, so an induced dipole. So we have ion-induced dipole as the strongest of these. So this would be something like sodium ion interacting with the induced dipole of a large polarizable thing. So that sodium ion is going to attract the electron density we have here, getting a partial negative area, partial positive area, that positive of the sodium, the partial negative of the iodine will interact with each other. Next we have, and your ion-induced dipole is between, so this is a weak force, it's between 3 and 15 kilojoules per mole. Okay. Then we move on to dipole-induced dipole. So I try to keep these in line. So with this one, we have a polar molecule interacting with a nonpolar molecule. So something like, you would see this with carbon dioxide in water. So carbon dioxide itself is a nonpolar molecule due to symmetry, but we can induce a dipole. So we actually induce a dipole like that. There's our partial negative, our partial positive, and then that will interact with something like water. Like so. So this is how you can get small nonpolar molecules dissolved in stuff like water. This is a weak interaction. It's between 2 and 10 kilojoules per mole. And then our lowest energy is going to be induced dipole, induced dipole. So we have 2 nonpolar molecules. They shift their electron density, causing a partial positive and a partial negative end. So we'll see these with large nonpolar molecules the most, or they'll be the strongest in long nonpolar molecules. The more electrons we have, the more polarizable, right? The more polarizable, the more electron density we can push in one direction or another. So with your induced dipole, the longer your molecule, the more directional you can get in induced dipole, so the stronger that interaction, the more electrons, so the more atoms, or the further down the periodic table. All of these things will result in a larger induced dipole. Okay, so again, we can push electron density in one direction or another, get a partial negative area, a partial positive area, and that will then interact with another molecule. Once it's got an induced dipole, it can induce another one. Like so. So as this comes in contact with this other nonpolar molecule, it will cause its electron density to shift, inducing a dipole. That looks like this, for a partial positive end and a partial negative end. And those will interact. Voila. Okay, so our strongest is the ion dipole, our weakest is induced dipole, induced dipole. As I said, as we increase our molecular weight, we're going to increase the induced dipole interactions. As we increase our surface area, we're going to increase our induced dipole ability. So a lot of our properties of liquids are dependent upon how significant the intermolecular forces are within those liquids. So it determines whether or not we can dissolve things. It also determines the properties of pure substances. So with pure substances, the greater the molecular weight, the higher things like boiling point and surface tension or melting point, all of those things. The more surface area, so the longer a chain versus kind of a bulky chain, or bulky molecule, the greater the boiling points, the greater our different properties that we get within these, like I said, surface tension or capillary forces. All these type of things are going to be affected by the magnitude of the intermolecular forces. So with an induced dipole, depends on molecular weight, depends on surface area of the molecule itself. With hydrogen bonding and dipole-dipole interactions, it doesn't matter about your molecular weight. It just matters how much of your molecule is polar. So the more polar, the greater that intermolecular force. And with a dipole, the greater the difference in electronegativity, the greater the dipole, the greater the difference in area. So the charge distribution, the further you can get that charge distribution, the greater the dipole as well. Okay. So some of the properties you guys should understand that are affected by intermolecular forces include boiling point. So intermolecular forces and properties. So we're thinking about stuff like boiling point and melting point. So stronger intermolecular forces, we're going to have greater boiling points and melting points. If we are dealing with non-polar molecules, so greater molecular weight or greater surface area, this will also give us greater boiling points and melting points. Okay. Other things, we're going to look at viscosity. Viscosity. So this is the resistance of a liquid to flow. Greater intermolecular forces, greater viscosity. But the shape of the molecule actually will have greater effect. So the more likely a substance can entangle within itself, the greater the viscosity. So really great or large surface area, so long molecules will have a lot of viscosity. And then things that have lots of hydrogen bonds will also have great viscosity. So more surface area, greater viscosity. And again, this is more important than the intermolecular forces, but something like hydrogen bonding, more hydrogen bonds. So if you have something that is long and lots of hydrogen bonds, it'll have a lot of viscosity as well. Next, we think about surface tension. This is when your surface has an elastic tendency. So it's because the surface of the molecule is actually smaller, or surface of the substance is smaller, because intermolecular forces are pulling those molecules in. So this is going to be something where the greater the intermolecular forces, or the imbalance of intermolecular forces between the surface or the substance itself, the liquid itself, and what it's in contact with. So it's going to be the difference between the intermolecular forces of the liquid versus the surrounding medium. In general, that surrounding medium is going to be air. So the more polar your molecule, the less like air it's going to be, so the greater the surface tension is going to be. Then we have capillary action as our last one. And this is the interplay between adhesive forces and cohesive forces. So here you've got your cohesive forces, so when liquids resist separation, and adhesive forces is going to be your attractive forces between different molecules. So things will go up a capillary because things like water will go up a capillary because they like the sides of the container that they're in, or the glass, and then it also likes itself. So it is attracted by the sides of its container, then it's attracted to itself, and then the sides of its container, and it will go up. The more narrow the tube, the greater the rise of the liquid. Okay. Sorry, I'm just looking through these PowerPoints, making sure I'm hitting all the things. We looked at the different changes of state in lecture number 2. So you need to know your phase changes, what they're called. Knows phase changes. So you should know that going from a solid to a liquid is melting, going from a liquid to a gas is boiling, going from a gas to a liquid is condensation, going from a liquid to a solid is freezing, going from a solid to a gas is sublimation, going from a gas to a solid is deposition. Those are the terms that you should know. You should also know that going from a solid to a liquid to a gas, or a solid to a gas, requires energy. Going from a gas to a liquid to a solid, or going from a gas to a solid, releases energy. You should also know the terms heat of fusion, heat of vaporization, or heat of sublimation, also called enthalpy of fusion, enthalpy of vaporization, enthalpy of sublimation. So these are the heats or energy that's required to either melt a solid, evaporate a liquid, or sublime a solid to a gas. If you are going from solid to liquid, liquid to gas, solid to gas, those heats of vaporization will be positive. If you're going the opposite way, they will be negative because energy is released in those processes. So no phases, no delta H fusion, delta H vaporization. Don't know why it does that all the time. And then delta H sublimation. We've never used delta H sublimation, so we probably won't. You should be able to do heating and cooling curves. And you should be able to calculate heat changes when doing phase changes or changing temperatures. So when we have a phase change, that'll be Q is equal to your mass times by your delta H of whatever change that happens to be. That delta H will be positive if we're adding in energy. That'll be negative if we are releasing energy. So going from a solid to a liquid, going from a liquid to a gas, your delta H will be positive. Going from a gas to a liquid to a solid, that delta H will be negative. You can also, if your delta H is given in moles, so if your delta H is given in kilojoules per mole, you'll do Q is equal to moles times by delta H molar. So make sure you can convert between grams and moles, and make sure that you pay attention to your units with these. You can also, so this is for our phase changes themselves. For our temperature changes, we're going to have Q is equal to mass times by specific heat times by delta T. That specific heat is going to be phase dependent. Okay, if you draw out a phase diagram, or a heating curve or cooling curve, you can see this a little bit better. You also may have it as a molar heat. So you'd have Q is equal to moles times by your molar specific heat times by delta T. Okay? So again, just pay attention to your units. We looked at vapor pressure, so you need to know what vapor pressure is. And how it is related to boiling. We looked at calculating vapor pressure. So make sure that you can use the Clausius-Clapeyron equation. With the Clausius-Clapeyron equation, you'll either be doing, Clausius-Clapeyron. You'll have ln PVAP, which is our vapor pressure. PVAP is the vapor pressure, equals negative delta H. That's going to be our enthalpy of vaporization divided by R, where your R is your gas constant, equaling 8.3145 joules over moles times by Kelvin. Pay attention, a lot of times your enthalpy of vaporization will be in kilojoules, while your R is going to be in joules, so pay attention to those units. Times by 1 over T in Kelvin plus C. So that's the general Clausius-Clapeyron relationship, but we almost always look at it in this form. ln P1 over P2 is equal to negative delta H over R times by 1 over T1 minus 1 over T2. Again, your P's are going to be your vapor pressure, your delta H is going to be your enthalpy of vaporization, your temperatures are going to be in Kelvin. And pay attention to the units here. Okay? So be able to use that equation, be able to draw a phase diagram, and interpret. It's more important that you can draw a heating and cooling curve, but you should know what the general layout of a phase diagram is. You should know what the melting, freezing equilibrium line is, what the vapor liquid equilibrium line or vapor pressure curve is. You should be able to recognize the sublimation deposition equilibrium line. You need to know where the triple point is. You need to be able to locate where the melting point is, or the normal melting point, the normal boiling point, and your critical point. So all of those things are things you should know. You should know what a supercritical fluid is. So let me real quick. So need solid liquid equilibrium line along with the liquid vapor equilibrium line, and then your solid vapor equilibrium line, where your liquid vapor line is also called your vapor pressure curve. So from our Clausius-Clapeyron equation, we can actually plot that. Okay, and then you need to know where the triple point is. critical point, normal boiling point, normal melting point. So these are our boiling points and melting points at 1 atmosphere. And then our states. You should be able to look at that and define where the states are, remembering that our solid is going to be low temperature, higher pressure. Our vapor is going to be higher temperature, lower pressure. Our liquid is going to be medium temperature, higher pressure. As the solid and liquid are more condensed phases, so they exist at higher pressures. Our vapor is a less condensed phase, so it exists at lower pressure. We also have supercritical fluids. Supercritical fluids have gas and liquid-like properties, so they are low viscosity, high density, they can effuse through a solid, and they can solubilize solids. So just understand what a supercritical fluid is. And also you want to be able to recognize what liquid crystals are. With your liquid crystals, understand that they have a intermediate phase that's temperature dependent, where you go from a random ordering of your liquid particles to an ordering phase that looks almost like a crystal. And your liquid crystal itself can be a pneumatic liquid crystal, cymatic liquid crystal, or a cholesteric liquid crystal. So just know those terms, at least have recognized them and kind of know what they look like. Okay, and that's it for chapter number 11. We're going to move on to chapter number 12. Let's go down here. So chapter 12 is our solids. With our solids, we're talking about the different types of solids, so you know your types. So this includes metallic, ionic, covalent network, and molecular. So with those, know their properties. From a description of a crystalline solid, you should be able to tell what type of crystalline solid you have. You should also know the difference between a crystalline solid and a amorphous solid. So you should know that your amorphous solids, that's your irregular arrangement. So those are going to be glasses, polymers, stuff like cotton candy. So they're usually formed through supercooling or super rapid cooling, and they don't have time to form that crystalline lattice, although some things just naturally form amorphous solids. And then your crystalline solids, that's a regular ordered arrangement of atoms, ions, or molecules. Like I said, you should know your different properties. So molecular solids are low melting, they're soft. Metallic solids are going to be malleable, ductile, conductive, and they have melting points that are variable depending on how many electrons are shared between them. Ooh, sorry. Ionics are going to be hard, brittle, and high melting, and they are going to be non-conductive in the solid state. However, they will be conductive in the liquid state. And then our covalent network are going to be high melting and hard. A lot of these are going to be semiconductors, so they have conductivity about them. Molecular solids also are non-conductive. So our molecular solids and our ionic solids are going to be non-conductive. Our metallic solids are going to be conductive, and then our covalent network are usually semiconducting. So be able to describe those properties and be able to look at properties and determine what type of solid you have. So we want to predict our solid type. Understand MO theory for metals and semiconductors. For metals, semiconductors, and insulators. So we're talking about band theory with that. So know your conduction band, know your valence band. And then your band gap. EG is band gap. So know your band gap and how it forms, and how that is related to the conductivity of the solid. You need to understand the electron C model for a metal. So with your electron C model, you've got a bunch of cations, metal cations, and a sea of electrons, and that sea of electrons is shared with everybody, and that allows it to be conductive because of those sea of electrons. It also allows it to be malleable and ductile because it has the ability to shift without causing any disruption in charges. You should know crystalline solid terminology, so you should know what a lattice is, you should know what a unit cell is, you should know what lattice points are, you should know what coordination number is, you should know what a Z number is, you should know what an edge length is. So lots and lots of crystalline solid terminology. So unit cell, lattice points, lattice. You should know your different types of lattice points. So your face, body, corner, which are the ones that are the normal ones, and then there's also the edge piece. So know all of those for your lattice points, your lattice itself, your coordination number, your Z number, and edge length. Since we're talking about cubic cells, we only talk about A in terms of edge length. You should know your different types of unit cells. So we only look at cubic, but we should know or recognize the names of other ones. I do not expect you guys to know how A, B, and C are related and how alpha, beta, and gamma are related in any other cell besides cubic. So for your cubic, you've got A equals B equals C, so your edge lengths are all equal, and then alpha equals beta equals gamma, so the angles within the unit cell itself. So if we think about, so here's our cube. It's a horrible cube, sorry y'all. So here's our cube, and we have actually color a different color. So we're talking about right here. So I'm going to bring that out so I can write a little bit better. So this big thing is what just came from right there. Right? So we have C, B, A, alpha, beta, and gamma, and our different unit cell types will have different values for A, B, and C, or different relationships between A, B, and C, different relationships between alpha, beta, and gamma. With our cubic, A equals B equals C, alpha equals beta equals gamma. Something like tetragonal, A and B will be equal, while C will not. Alpha, beta, and gamma will be equal, so it'll kind of be an elongated cube, so it'll be higher. And then orthorhombic, A, B, and C are all different. Alpha, beta, and gamma are still the same, so it'll be elongated in two directions, so on and so forth. So you should know your different cell types. So you should know you should know the 3D and 2D, although I won't ask you the 2D on this test, but you might need 2D later on in life. And then we're going to move on to metal crystal packing, so how atoms pack within a metallic solid. So this is when we start to look at our different lattice points. So if we have a metallic solid, it'll be simple or primitive, cubic, body-centered cubic, or face-centered cubic. With our simpler primitive, our Z is equal to 1, so we have one atom in there. It looks like this. Actually, I'll go on to the next page. So our simple looks like this, where we have an atom on each of the corners. There are 8 corners, and each accounts for an eighth, so our Z is equal to 1. Our coordination number is equal to 6, and our A is equal to 2R. That A value will be given. So whatever atom you have in there, if you multiply its radius by 2, it'll be your edge length. So next one is body-centered, so this is primitive. Next is body-centered. Body-centered. That looks a little bit better. Has the atoms on the corners. And then it has a body centerpiece. So a piece all the way in the center. Like so. They're all the same. Don't let my shading in confuse you. So we have one atom for the 8 corner pieces, and then we have 1 in the center, so Z is equal to 2 in this case. So our number of atoms within here are 2. Our coordination number is equal to 8. And our A, which is right here, is equal to 4R over the square root of 3. Next we have cubic closest packed or face-centered. So our cubic closest packed, we have atoms on all of our faces and atoms on all of our corners. I'm going to do my best to try and draw this. It's not going to be perfect. Sorry, in advance. So each corner, and then each face. Each face accounts for half an atom. Each corner accounts for an eighth of an atom. So for our corner, we have a Z of 1. For our faces, we have a Z of 3. So we have a total Z of 4. Our coordination number here is going to be 12. And our edge length is going to be 2 square root of 2R. As far as packing goes, our primitive is going to be the most empty. So the least efficient packing of atoms. And then our face-centered is going to be the most efficient packing. I don't know why it won't. Efficient packing. Okay. We also looked at hexagonal closest packed, but it is unnecessary to know that. For the primitive, if it's just a metallic, the packing will be 52%. So our packing efficiency. For our body center, the packing efficiency is going to be 68%. And for our face center cubic, which has the greatest packing efficiency, is going to be 74%, which is the same for hexagonal closest packed. We also looked at alloys here. For our alloys, you should know the types of alloys that we have. So in general, an alloy is a solid solution. The only instance of an alloy that's not a solid solution is an intermetallic compound, which is arguably not an alloy, but we looked at substitutional alloys, where we have one element taking the place of a metal atom, and they're going to have, so one metal atom will take the place of another metal atom, and the two metal atoms will have similar atomic radii. We have interstitial. With our interstitial, we have a solute atom that is filling in the leftover empty space of your initial solute atom. Your solute atom must be significantly smaller than your solvent lattice atom. So it'll fit in the interstitial space left over. And then heterogeneous. With our heterogeneous, the components are not uniformly distributed. This is usually gotten when you cool something really quickly, so we have different phases throughout. And then lastly, we have our intermetallic compound. So the other ones are not compounds. They're just, you throw in some other stuff into a already existing metal lattice. With your intermetallic compounds, we make these compounds that have distinct properties and definite compositions. So with alloys, you can have, you roughly have percentages of different things to produce an alloy. With an intermetallic compound, you have a specific whole number ratio of different atom types. And it is a metallic compound, so it's two metal atoms making a compound type. Okay. We started, after that, starting to look at different calculations. We looked at unit cell densities. And what we want here is we want grams over centimeters cubed. Okay, so we have the mass of our atoms in the unit cell. And this is going to be in grams, divided by our volume of our unit cell. So this is going to be A in centimeters cubed. Okay? So you can look at this as your Z number times by your molar mass divided by Avogadro's number, all divided by A in centimeters cubed. Okay? This is if we have metallic or elemental. If we have ionic, we're going to take Z plus times by its molar mass plus Z minus times by its molar mass a little bit better. Z minus times by its molar mass divided by Avogadro's number, and then the whole thing is going to be divided by A in centimeters cubed, and this A is based on the anion. And we'll talk about that in just 1 second. You can also look at packing efficiency. Packing efficiency is going to be volume of your atoms divided by the volume of your unit cell. And it doesn't matter what unit you use for R as long as you keep consistent between your two. So for metallic or elemental, this equation will be your Z times by 4/3 pi R cubed, right? And this will be divided by A cubed. Okay? For your ionic, this will be Z plus times by 4/3 pi R cubed plus Z minus times by 4/3 pi R cubed. Okay? And then it'll all be divided by A cubed. Let's look a little bit more at ionic solids. For your ionic solids, you need to understand their properties, and you need to understand that we're dealing with a little bit different packing with this. So your anions are going to form those regular packing arrangements. So anions will form either a primitive cubic or face center cubic arrangement. And then your cations will fit in the holes left over. And the type of arrangement that you'll get will depend on the size of your cation versus the size of your anion. So you'll look at radius ratios, so make sure you look at what a radius ratio is. Remember how to calculate them. You have your different radius ratios after you calculate it. If you have between a radius ratio of 1 to 0.732, you have a cubic hole, which a cubic hole basically looks like a body-centered cation piece. So we have our anions, which I'm going to show as blue. So you have your anions making a primitive cubic cell. And then you have your cation, which is significantly smaller, in the center. So in the case of a cubic hole, it's not that much smaller, right? Because we're taking our cation radius divided by our anion radius, and it's somewhere between 0.732 and 1, so they're similar in size, your cation and your anion here. Okay? If you calculate out your radius ratio and you get a value between 0.732 and 0.414, you have an octahedral hole. So your cation will fit in an octahedral hole. So this occurs when we have a face center cubic arrangement of our anions. we've got a face-centered arrangement for our anions, and then our cations are going to go in the spaces left over, so they'll be on edge pieces. And they'll be as a body piece. Okay? Within a face-centered cubic, there are a total of 4 octahedral holes. So if we have half of them filled, we have a Z equal to 2, all filled. All right, we have a Z plus. If they're all filled, we have a Z plus equal to 4. Okay. So kind of with our octahedral holes, if we have all of them filled and we're in a face-centered cubic, that means our cations will have a Z number of 4, our anions will have a Z number of 4. So we'll see that in a 1-to-1 ratio, such as in sodium chloride. Our last one, our last radius ratio we're going to look at is going to be between 0.414 and 0.225. In this case, we've got a tetrahedral hole, which is the smallest type of hole. With a tetrahedral hole, again, we've got our face-centered cubic. I'll draw this a little bit bigger because we have more. In this case, there we go. So we've got our anions. Again, these are going to be in a face-centered cubic arrangement for our anions. And then our cations are going to fit. I'm going to try my best to kind of draw this in these kind of boxes within here. Okay, so we've got this little box in here. They kind of fit in, and they're like right here. So to kind of draw the box a little bit better, let's look at this real quick. So we've got our anions kind of here, 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 and here, and then in the center of that, we've got our tetrahedral. So if we take our box, our whole unit cell, and we divide it in 8, we have 8 areas, or 8 tetrahedral holes total. So if we have half filled, we have a Z plus equal to 4. All filled, we have a Z plus equal to 8. Okay? So as we go, as we go from our cubic hole to our octahedral hole to our tetrahedral hole, the holes are getting smaller. And these are formed when we have a smaller radius in reference to our, or smaller cation radius in reference to our anion. some other things I want to point out about this. If we have a cubic hole, the cation's coordination number is going to be equal to 8. If we have an octahedral hole, our cation's coordination number is going to be equal to 6. And if we have a tetrahedral hole, our cation's coordination number is going to be equal to 4. I just expect you guys to know the cation coordination number. You don't need to know the anion coordination number. So you should be able to calculate out what type of radius ratio you have, or what radius ratio you have, and then figure out what cation hole you have, or look at a structure and figure out what cation hole you have. And then you should be able to figure out, the type of unit cell you have, looking at your structure, or figure out your empirical formula for your ionic structure. Lots and lots of different things you need to know to do for this. Figure out you should also be able to do density and packing efficiency for ionic cells. Okay, next we talked about covalent network solids. We talked about band theory. So you guys need to know what a covalent network solid is. So this is going to be where we have a covalent network. So we have one atom covalently bonded to another atom, and this goes out in all 3 directions. Like an ionic solid, but instead of having ions, we are going to have atoms. So these are going to be either nonmetals or metalloids. You should be able to look at a structure and determine if it's going to be metallic, ionic, covalent network, or molecular, just by looking at structures and what type of bonds it'll make. Silicon almost always makes covalent network solids. Your metalloids will make covalent network solids. The only time that you will have a silicone that does not make a covalent network solid is if there's a hydrogen somewhere in there. And then carbon by itself makes a covalent network solid. So know if something's going to make a covalent network solid versus a metallic solid, ionic solid, or molecular solid. You should be able to describe band theory. And we already talked about that, so I'm not going to go any more into that. But how conductors, semiconductors, and insulators differ, you should be able to look and determine if we have something that is going to make a semiconductor. With your band gaps, you should be able to determine kind of how band gaps are going to be when you look at different types of semiconductors. So if we have elements located higher up on the periodic table, those are going to be ones where you have enhanced orbital overlap, right? Because our orbitals are closer to the atom itself, because the electrons are closer to the atom, or nucleus. So that's going to lead to larger splittings between your bonding and antibonding energies and a greater band gap. So your band gaps. So higher up on periodic table, greater band gap. And then if the horizontal separation increases, this will lead to an increase in electronegativity difference and bond polarity, and an increase in your band gap. So greater horizontal difference will lead to a greater band gap. Okay, so you should be able to look at materials and determine how their band gaps are going to differ. You should know how semiconductors dope. You should know what an N-type and P-type semiconductor are, and how you form them. Okay? An N-type, you're adding an element into your structure that has more valence electrons than the host material. A P-type, you're adding an element which has less valence electrons into your host material. You can do this with elemental semiconductors such as silicon. So you can add phosphorus into silicon to produce an N-type, or gallium into silicon to produce a P-type. Or if you have a binary semiconductor, so if you have a group 2B 6A semiconductor such as zinc telluride, or a group 3A 5A semiconductor such as indium phosphide, you can also determine what type of, you can determine if you're going to make N or P types in those as well, just thinking about how valence electrons, if you're adding in something with more or less valence electrons as to what type of semiconductor you're going to form. You should know what a polymer is. You should be able to draw. So with your N and P type, predict elements to form N and P type. Your polymers. With your polymers, you're looking at monomers and polymers. You should know how to make a addition polymer and how to make a condensation polymer. So you should be able to look at these and determine if you've made an addition polymer, if you made a condensation polymer, or you should be able to determine, you should be able to predict what type of polymer you are going to make. I don't really care much more about polymers. Nanomaterials. You need to do energy calculations with these. So you'll be given this equation, but E is equal to hc divided by your wavelength. Energy will be in joules. Wavelength will be in meters, right? Because H is in joules times by seconds. C is in meters over seconds. So we need joules and meters. So make sure you can convert into joules. Make sure you can convert into meters. Understand how band gap and particle size are related. Know the different types of nanostructures. So we've got our quantum dots, nanometals, and then the different types of nanostructured carbon, C60, carbon nanotubes, graphene, and nanodiamonds. And again, calculations of their energy or calculations of wavelength based on band gap energy. Okay? Let's move on to chapter number 13, our last chapter. So our solutions chapter. In this one, we're starting to do a little bit more calculations. So there wasn't a lot of calculations here. You should know the difference between a solution, colloid, or suspension. You should be able to tell me the components of each, and the particle size of each, and the appearance of each. And you should be able to give an example of each. You should be able to determine how something solubilizes. So you should be able to relate solubility and intermolecular forces. So like dissolves like. Keep that in mind. Like intermolecular forces will result in solutions. You need to know what entropy is and how it is related to the solution process. You should know what's going on during the dissolving process. And And you should know your H1, H2, and H3. So you should be able to do a somewhat calculation of H solution when you take H1 plus H2 plus H3, right? So this is going to be your solute. So breaking solute interactions, this is going to be solvent. So breaking solvent interactions, it doesn't matter which one's H1, doesn't matter which one's H2. And then your H3 is going to be forming solute-solvent interactions. So these will be positive. And then this one will be negative. We want this to be negative or small positive, because in order to make a solution, your delta G, your Gibbs free energy, which is delta H minus T delta S, enthalpy of solution, entropy of solution. For us to form a solution, your delta G must be negative. That's spontaneous. So you should be able to use this equation to describe what's going on in the solution. Entropy itself, that randomness that occurs when we make a solution, that'll always be positive. So when the entropy term is positive, that will make this negative, right? And then if we have an enthalpy that is negative or just barely positive, we'll be able to have a delta G that is negative and we'll make a solution. We can increase our entropy term by increasing temp. Which is why we can increase solubility with increasing temperature. You should be able to look at intermolecular forces and determine if you will make a solution. And describe it energetically, what's going on. You should be able to determine if you have a dissolving process or reaction. If you see two substances together, that'll do one of the reactions that we know, so redox, precipitation, acid-base. So if you see things going together that you know will do a redox or a precipitation reaction or an acid-base reaction, those would be reactions. So we add an acid and a base together. That's a reaction. We add in metal to a metal salt, or to a salt solution. That could cause a redox reaction. If we see a solid form, that's a precipitation reaction. So remember those reactions from back in 1211. So these are all reactions. Just adding two things in with similar intermolecular forces is dissolving. So if we add two nonpolar things together, it's going to dissolve. Two polar things together, it'll dissolve. Ionic compound into water, that's a dissolving process. If we see gas formed, that's going to be a reaction. So keep those things in mind. You should know our different types of solutions. So we have unsaturated, saturated, and supersaturated. So you should be able to describe these in terms of equilibrium. You should understand the factors that affect solubility. Of course, we've got intermolecular forces, similar intermolecular forces, similar solubilities, or we get solubility. But we also have other things that impact solubility is surface area, temperature, and pressure. If we increase temperature, we're going to increase solute or solid solute solubility in a liquid. If we increase pressure, we're going to increase gas solubility in a liquid. And if we increase our surface area, then we're going to increase our rate of solution formation. For our pressure versus solubility, we think about Henry's law. So greater pressure over a solution, greater gas solubility. So solubility is equal to our Henry law's constant times by pressure, and this is going to be partial pressure of gas. Remembering that our pressure of our gas is equal to our atmospheric pressure times by our mole fraction of our gas. Okay. We can also use this relationship, S1 over P1 is equal to S2 over P2. So another way we can utilize Henry's law to see how pressure affects solubility. We need to know our concentrations. So you should be able to figure out molality, which is moles of solute over kilograms of solvent. We have molarity, moles of solute over liters of solution. We have percent by mass. This is a mass unit over another mass unit, the same mass units, times by 100%. So this could be grams, grams, or milligrams over milligrams, or pounds over pounds. It doesn't matter. As long as you keep the mass unit the same. It could also be a liquid one. We could do liters over liters, milliliters over milliliters, whatever you want. Then we have our parts per. So we have grams over grams times by a representative quantity. Or it really, again, just like with the percent by mass, the parts per can be any units as long as they're the same on the top and the bottom. The bottom in both of these is going to be solution. The top on both of these is going to be solute. So solute mass over solution solute mass over solution mass times by either 100% to give you percent by mass, or a representative quantity to give you parts per. So parts per 1,000, you multiply by 1,000. Parts per million, you multiply by 1,000,000. Last, we have mole fraction. So mole fraction is going to be your moles of substance over your total moles. It doesn't matter, just any mole amount over, so if whatever you're looking for the mole fraction of, you divide that number of moles over the total moles. Okay, and then last part of chapter 13, we start talking about colligative properties. So you should know what a colligative property is. So you should know them and how they work. How do we have vapor pressure lowering? How do we have boiling point elevation? How do we have freezing point depression? How do we have osmotic pressure increasing? You should also know what Van Hoff factor is and how to calculate it. So this is our particles of solution, or moles of particles of solution divided by moles of solute dissolved. So sodium chloride, something ionic, will have more, a greater I value than a covalent compound. Covalent compounds besides acids and bases will always have an I equal to 1. So know how our solute is going to affect our different colligative properties, be able to do calculations such as using Raoult's law. So with Raoult's law, you have the vapor pressure of your solution equaling your solvent's vapor pressure times by your mole fraction of your solvent. Remembering that the mole fraction of your solvent will be equal to 1 minus the mole fraction of your solute. Okay? So be able to do the calculations using Raoult's law. Also, if you have a volatile solute, so Raoult's law you use for a non-volatile solute, but if you have a volatile solute, you're just going to take PA and you're going to add it to PB to give you your total vapor pressure I guess, actually, right, I'm going to write that just a little different so it makes a little more sense. So if we have two volatile things, two volatile liquids you're adding together, you're going to figure out their vapor pressure by taking their regular vapor pressure and multiplying by their mole fraction. And then adding those two together to get your total vapor pressure. Understand deviations from ideal P. So know what an ideal solution is. And then deviations from ideality. So negative or positive deviation. And why it occurs, how it's related to intermolecular forces. Okay. You should be able to do boiling point, freezing point calculations. So know what boiling point elevation is, freezing point depression, and how they work. So with your boiling point elevation, so this is related to vapor pressure lowering. Know how. Okay, so our boiling point elevation, we solve for that by taking our Van Hoff factor times by our molar boiling point elevation constant times by molality. Our freezing point depression understand how that works. Freezing point depression is equal to negative I, because it is depression, times by our molar freezing point elevation, or sorry, depression constant, times by molality. Know how to solve for your Van Hoff factor. Make sure you can do that. Make sure you can do all of these calculations. Also be able to solve for molar mass using this information. Okay. We're also going to look at so know what osmosis and osmotic pressure is. So understand how those work. We have our equation for osmotic pressure is equal to our Van Hoff factor times by our molarity times by R, 0.08206. So our gas constant times by temperature in Kelvin. Okay, so be able to do osmotic pressure calculations and solve for molar mass using these equations. Know what isotonic, hypertonic, and hypotonic solutions are? Understand what ion pairing is? So when ions kind of join together, lowering our Van Hoff factor. So something like sodium chloride, an ideal Van Hoff factor for this would be 2. But as we increase concentration, we decrease that value. Okay, and that always occurs. You guys should understand what a colloid is. You should know what the Tyndall effect is. You should know what a hydro and hydrophobic and hydrophilic colloid is. Okay. You should understand what Brownian motion is and how it is related to particle size in a colloid, and how it's related to the mean free path. And that is everything for this chapter, or this test rather. So good luck. Let me know if you have any questions.